Welcome back to the 7th video now about the details of the A1335 precision Hall effect angle sensors. In the last video, we made our first steps towards linearization. That is somehow correcting the errors we have when we are rotating here, measuring the angle. And the angle we are measuring is not quite the angle we are setting our axis to. And these first steps were: 1, setting a 0 position for our angle measurement. I mean, I've built in here a very distinctive detent giving us a mechanical 0 position. So that mechanical 0 position actually delivers us a 0 output of our angle measurement. And second, setting the direction of rotation. That is, the angle for both sides increases when I turn the wheels away, or the axis away from me. Card here, link in the description. Today I want to actually correct the errors we have here on our angle measurements using the linearization features of the A1335. Enjoy! The A1335 offers you two different kinds of linearization. First, you have the segmented linearization, and second, there is a harmonic linearization. And by the way, last time we set the pre-linearization rotation using the LR flag and the pre-linearization 0 offset, which is stored in the segmented linearization offset field. You activate the different kinds of linearization, either harmonic or segmented, by setting bits inside the algorithm enable flags. For harmonic linearization, you of course set the HL harmonic linearization bit, and for segmented linearization, you set the SL segmented linearization bit. We've already written the code for setting all the algorithm enable flags within the SRAM register address 06 in the previous video. So we already have the tools to set either the segmented linearization flag or the harmonic linearization flag in the SRAM. I should mention at this point that there is a note here, CLO, if both segmented and harmonic linearization are to be used. I think that's a copy and paste error here in the programming reference, because I cannot find a mentioning of a flag LO anywhere else in here. Anyway, we will see later that really setting the parameters for segmented and harmonic harmonization at the same time is quite impossible. So yeah, that's probably just an error in the datasheet. So, what's harmonic linearization then? Let's start by describing the problem we want to solve with it, and that's measurement errors. By the way, segmented linearization solves, of course, the same problem. On my x-axis, I have the actual angle at which the magnet is oriented relatively to our sensor. That goes, of course, from 0 degrees to 360 degrees, 360 degrees being equal to 0 degrees, again, because we are working on a circle here. On my y-axis, also going from 0 degrees to 360 degrees, I have the angle that is measured by the A1335. Ideally, the actual angle and the measured angle are of course the same, giving us here that linear curve, and that's why the whole thing is called linearization. In practice, the measured angle is of course not equal to the actual angle. There are many reasons for that. I mentioned many times before, as an example, the misalignment between the magnet and the sensor. And especially in that case, you will get a sinusoidal deviation from the linear curve. And if you subtract from our actually measured values the ideal values, so the linear values, you get an error curve, which is, of course, in that case, also sinusoidal in nature. And here comes finally the harmonic part. We take our error curve here. We would have, of course, beforehand measured the error with some external devices and use a Fourier transformation to get that into the frequency and phase space of a base frequency with its harmonics. If we're talking about circular functions, it doesn't make sense to talk about frequency in hertz. Instead, we should talk about relative to the circumference of the circle, which is 2 pi or 360 degrees, wavelength. Just remember that wavelength is just inversely proportional to the frequency. The base wavelength the A1335 is using is, I guess, I'm not quite sure because it's never mentioned explicitly anywhere in the documentation, 720 degrees or 4 pi. That is, that function or sine wave would go 2 times around the circle until it repeats itself. And from there on, we have 14 harmonics of that frequency or wavelength. So that would go from 720 degrees to 360 degrees and up to 48 degrees. And I've just drawn here, our base wavelength of 720 degrees. Then the next harmonic here at 360 degrees, the dashed line, and then I have here the fourth harmonic of 180 degrees. That's the dotted line. You store the result of your Fourier transformation in the SRAM's location OC21A. And there you have, for the base frequency up to the 15th harmonic, 2 fields available, one for the phase for that frequency or wavelength we used, and 16-bit for the amplitude. After you stored all this in the SRAM, the A1335 can use that information to simply add up all your 15 wavelengths, probably shifted by the phase and multiplied by the amplitude, to get to an error curve, which it then subtracts from the measured values to get to our ideal linearized curve. Sounds extremely complicated, but Allegro is providing a software development kit to do all those calculations properly, and to get the actual values you have to write to the SRAM for a certain error curve. Nevertheless, it's a bit too complicated for me because you need to take a lot of measurements here. But it's the recommended method for correcting errors in off-axis applications. Remember, in one of the in the basic video, I think I talked, a card here, link in the description, I talked about that the A1335 is totally capable of off-axis measurements. That is, the magnet is really beside the sensor, rotating around it, or the sensor is rotating with the magnet in a fixed position. And that produces a whole lot of sinusoidal error signals here. And there's nothing better than a Fourier transformation, or than a reverse Fourier transformation, to get these errors out. Now let's talk about a segmented linearization. There we have actually two variants available. One using external encoder readings and the other internal A1335 angle readings. And that's controlled by the flag LS. That flag is of course also included in our algorithm enable 16-bit word here in the SRAM. It's called the segmented linearization select and it's self-explanatory, mostly, so it determines the reference index axis for evaluating signal eccentricity when segmented linearization is being used. References angles sampled in segments of 22.5 degrees, when moving in even steps as measured by an external encoder set SL to 0. This is the most common method, I already mentioned that, initialized also by the EEPROM field LS. So, how does the whole thing work? We start out like with the harmonic linearization with our little diagram here. So 0 to 360, our actual angle, or as measured by an external encoder, like for example with something like that. And then we have here again from 0 to 360 degree the measured angle by the A1335 internal encoder. That is our Hall element array. And ideally, yeah, linear curve, but in fact we have here of course an error. When using an external encoder, so the most common method, we simply turn the whole assembly to a known position using an external encoder. Something like that, for example. And then at this position we read what's the actual output of the A1335. And that's our correction coefficient, because if we give that information to the A1335, it knows if I get that reading, we are really at 180 degrees. So it can correct down to our ideal linearized curve. And you do that for every 22.5 degrees. That gives you a total of 15 correction coefficients here on that curve. And the A1335 will linearly interpolate between that points you give it. If you are using the less common option of utilizing the A1335's internal encoder, you turn your whole assembly until you get here a reading from the A1335 on one of the 22.5 degrees multiple positions. For example, here at 180 degrees. And then you take your external encoder and measure what's the actual angle. And you give that to the A1335 as correction point. Of course, again, for all the 15 correction coefficients. These segmented linearization coefficients are of course also stored in the SRAM. That's between the SRAM addresses 0C and 13. So here they are in green. Please note that there is an overlap between the harmonic linearization stuff and the segmented linearization stuff. So some memory locations are dual use here, depending on which linearization type you are using. And that in the end led me really to the conclusion that at least that chip, the A1335, can't really do both methods at once. The segmented linearization coefficients themselves are again only 16-bit unsigned integers representing 360 over 65536, so 2 to the power of 16 degrees. And within the SRAM addresses from 0C to 13, they are all over the place. So the two most significant bytes will hold the even numbered coefficients, and the two least significant bytes will hold the odd numbered coefficients. We already saw in the last part that exception here because the most two significant bytes at memory location 13 really contain the segmented linearization offset, and then coefficient 15 is stored in the two least significant bytes. Usually I would now continue with the code in the library and do a test with linearization. However, I'm feeling a little bit under the weather, so we'll have to cut it short here. I don't know if it's just the summer flu or the virus of unknown origin. Anyway, I already extended here my little jig or with an external encoder, so we can do precision angle measurements. And that's as soon as I'm well again, we'll continue with. Yeah, anyway, till then, bye.